then good
Ok,
luck.
ya está
Okay.
grabado.
Thank you very much.
Perfect.
Let me take the timing also from here. Thank you. All right. So, first of all, I would like to thank very much the organization of this very nice Congress. It's on one side, it's a pity we cannot be all together in Fortaleza, but on the other side, it's nice to see that the scientific work is going on despite the crazy period that we are all living in the world. So thanks once again for this invitation to give this lecture on smart materials and nanotechnology applied to civil engineering. Let me go to the content of the presentation. I will start with some introduction and motivation. Then I will just recall a few fundamentals of multifunctional nanocomposites for strain sensing that's needed for entering into the most important part of the presentation that will be devoted to presenting research results regarding smart concretes, most of all, and also more recent works regarding smart bricks. So the motivation, of course, is that we all know that our structures and infrastructure are exposed to several hazards, including natural disasters, degradation, fatigue, collisions, and so on. And what we all want to do as structural engineers is find ways of detecting criticalities well before they reach major failures or collapses. So we want to get an effective way to do preventive maintenance and so never reach the minimum acceptable threshold in terms of structural performance. So it's very important that we detect, locate, and quantify the criticalities well before any major collapse, as unfortunately happened even in recent times, including in Italy. So there are about two approaches to do that. One is non-destructive evaluation, and the other one is SHM. With my research group at University of Perugia in Italy, I would say that we are mostly working on the SHM framework, which means to acquire data continuously from a structure and then apply different techniques of data science to detect anomalies and possibly locate and quantify the criticality, and then have an efficient diagnosis, which means that we can take an engineering-based decision on what to do with our structure. But then in this field, we have some problems that we have to consider. With my research group, essentially, we have two research lines in SHM. One is the one I'm presenting you today, basically, that is related to the development of smart multifunctional structural materials. And the other track is developing algorithms for SHM using more traditional sensors and working on the algorithms like doing vibration-based SHM, artificial intelligence, data science, and so forth. Today, I will talk about smart materials, as I've said. So why do we need to include smart materials? Basically, because we have a big issue that sensors that we use in SHM, they do not measure damage. Damage is a change in material or geometric properties that adversely affects the structural performance, but of course, it's something that cannot be directly measured. Typical issues we have are also related to high costs, energy demand, complex data acquisition and analysis, environmental effects that have to be removed from the features that we use for damage identification, and then we need to include physics into our models for taking decisions. So why multifunctional materials? Because what we want is defining structural materials that generate a more direct response to a damage. We want the material itself to alert when there is a damage. So in doing it in this way, the sensors of an SHM system are basically naturally integrated in the structure because the material itself becomes a sensor, a distributed sensor. To do that, what we have to do is look at the micro or even the nanostructure of the material and engineer that structure in such a way to add novel functionalities and provide the material with an enhanced performance. An example of doing that is the diluting conductive nanoinclusions or nanofibers into a non-conductive matrix, for example, using carbon nanotubes, as you see in the bottom right picture from SEM inspection, and as I will show you later on in the presentation. So a little bit of physics that we need to recall. It's very simple. We just need to go back to the equation of monodimensional conductors to understand most of the work that I will show you. So basically, if we have a conductor, its electrical resistance is the resistivity of the material times the length divided by the cross section. And if this conductor is under monodimensional stress and strain, we have a relative change in resistance that is basically the sum of the relative change in resistivity plus the axial strain minus twice the transverse strain. If the material is a linear elastic material, then we can write this equation in the form that the relative change in resistance is actually proportional to the strain through the factor lambda that is called the gauge factor, that as a matter of fact is 1 plus 2 times the Poisson coefficient plus the relative change in resistivity per unit strain. So what happens typically in electric resistive strain gauges, for instance, is that this last term is not very important. So typically electric strain gauges have a gauge factor of about 2.1. Where if the Poisson coefficient is something close to 0.5, it means that we have the last term in the right-hand side of the equation that is about 0.1. Well, the idea in piezoresistive materials, in smart materials, in the smart materials I will show you, is trying to maximizing this last term that is associated to what's called the piezoresistive effect, and getting gauge factors that are much bigger than 2 or 2 point something, but can reach values up to hundreds or even thousands. How to do that is to create a conductive network of nano inclusions, nanofibers within the matrix, in such a way that an applied strain produces a change in the interactions between the nanoparticles, which means a strain in the overall resistivity of the material. It can be shown by the theory that the gauge factor is maximized for a specific content of nano inclusions that depend on the shape of the nano inclusions and the properties of the nano inclusions. That's called the percolation threshold. What's the percolation threshold? Is essentially the critical fraction of nano inclusions that makes the electrical conductivity jump dramatically from the value of the matrix up to the value of the composites. Let's say it passes from, the material passes from being an insulator to being a conductor. Here are a few literature examples of percolation. And in the top right, you see a percolating curve in terms of electrical conductivity versus content of multi-wall carbon nanotubes in a smart concrete application. And these results are typical results obtained in our lab, where you see that there is a big jump in conductivity. Note that the y-axis is in log scale, around 1% of nanotubes. What's very important to stress is also that we need a very good dispersion of the nanotubes if we want to achieve such a percolation. And this is very critical, as we will see later on. So let's come to the focus of the work. Most of the things I will show you are referring to smart concretes. What we call smart concretes are essentially cement-based materials that can be paste, mortar, or concrete, so with or without aggregates, that are made smart, strain sensing, self-sensing through the addition of different nano-inclusions. And the work I will show you is referring to the use of multi-wall carbon nanotubes. One big difficulty in dispersing nanotubes in concrete is that we need to disperse the nanotubes in water first, and then add cement and aggregate and so forth. And to disperse the nanotubes in water, we need a lot of attention, and typically we need sonication and sometimes magnetic steering. This, of course, is not suitable for large-scale production. So one way we proposed in the work by D'Alessandro and co-authors that you see referenced in the bottom right of this slide, to get rid of sonication was to use dispersants that are chemical surfactants that change the surface of the nanotubes and improve the possibility to disperse the nanotubes. Here you see some sketches, some figures from our lab, and note the difference in color that we have between a plain cement paste and a cement paste that has just 1% of multi-wall carbon nanotubes with respect to the weight of cement. The change in color is quite strong. Here you see some scanning electron microscopy images of nanotubes after dispersion in water, after water evaporation, as well as in the hardened cement matrix, where you see that the nanotubes form this sort of very nice spider network that creates the conductive ways through the material. The reason why we use multi-wall carbon nanotubes is because they have excellent mechanical and electrical properties. They have very high aspect ratios, and they have a small size. Essentially, nanotubes are cylinders of carbon atoms, one inside the other. And the multi-wall carbon nanotubes that we use have a cost that is absolutely compatible with an application in civil engineering. Of course, not in large amount, in small amount, but in critical situations, in critical locations of a structure, for sure the cost is compatible and competitive to what would be the cost of a traditional sensor. So you see here some of the properties of the nanotubes, where I point your attention to the very high tensile strength and the very high electrical conductivity. Here you see some pictures of nanotubes at increasing magnification, where you can have, look at the bottom left where you have the dimension, you can have the feeling of how small are these very thin wires of carbon atoms. So let's go to measurements. To measure the electrical resistivity of smart concretes, from the literature, we have two approaches, the two-probe method and the four-probe method. Both are direct current approaches. And the big problem we have in applying those methods is that since the material is a dielectric material, we have polarization. So typically we have an apparent increase in electrical resistance, like you see in the bottom diagrams, with time, because the material charges under application of a constant electrical field. Of course, the alternative is to do AC, to do alternated current, but then we cannot really go to multi-channel reading. So one main contribution we have done in the work by Donnie and co-authors was proposing a biphasic direct current measurement that keeps the advantages of DC but removes the polarization issue. So we can do multi-channel reading, but we don't have any polarization issue. And the way we do this is by applying the voltage input in the form of a square wave, where we have plus minus, for example, 2.5 volts in a single period of the square wave. And then for every period of the square wave, we just take one sample, one reading. And in this way, as you see in the bottom right, we completely remove the drift in time because of symmetry reasons, because the material stays the same time in the charge and the same time in the discharge part of the input. And the duty cycle of 50%, which means same time in the discharge and same time in the measure region, is actually the best value to get no polarization, as you see in these results. So we know how to fabricate these materials. We know how to measure. So let's see what happens if we apply a strain. Like, for example, here you see some test under compression on cubes of smart concrete. On top right, you see the applied strain in red. And in blue, you see the electrical response of the sensor. Let's call it a sensor. It's just a cube of concrete with 1% of multi-wall carbon nanotubes with respect to the weight of cement. If you compare this reading with what you get from strain gauges attached on the surfaces of the specimen, you get the comparison that you have in the bottom figure between the black line and the red dots, and you see there is a clearly linear relationship between change in resistance and strain. What is very nice is that we can also do this in dynamics, so do vibration monitoring with these sensors. We can apply a frequency sweep signal and in red, and you see the response of the sensor in blue. So the sensor can go high in mechanical frequency. And actually, if we look at the frequency response function of the sensor, so the amplitude of the response as a function of the mechanical frequency, we see that these sensors are almost linear. Linear would be that we have a frequency response function that is flat, equal to 1, while here we have a frequency response function that is a little bit increasing in frequency, which means that we have more sensitivity at higher mechanical frequency compared to the sensitivity we have at lower mechanical frequencies. Another notable aspect of these sensors is that the response to an harmonic mechanical load is periodic, but it's not harmonic. It has superharmonic components, as you see in the bottom right diagram of this slide. This, of course, is a drawback of these sensors that we will discuss later on. So let's come at applications. One first application we've proposed is to attach these sensors to existing structures to do, for example, OMA or vibration monitoring. We did this in DC by application to a reinforced concrete beam we have in the lab. And what was very important in this work we published in 2014 to really do vibration monitoring with these sensors is to use coaxial cables to cancel the noise. This was really the technological advancement that is, trivial in the field of measurements, but maybe it's not so trivial in the field of civil engineering. So if you don't do this with coaxial cables, there's no way you can cancel the noise. There is no way you can measure the vibrations. And here you see the experiment, the video, where you hear hits with a hammer over the reinforced concrete beam. There is the sensor attached at certain location. This student was helping. By the way, this student is now assistant professor in the United States, Laura Micheli. You see that when there is a hit, there is a change in the signal. That depends, of course, on where the hit is applied. Okay, let's go and analyze this signal. Well, actually, the video you have seen was not the one that was not referring to the sensor we used for the paper, but in any case, it was very similar. In this slide, you see the resistance in time. You see the drift due to polarization, very slow drift in black line. Then you see single hits of the hammer that give you this vibration, like exponential decaying vibration. If you apply a high-pass filter above 5 hertz, you get the blue signal. So you get no mean, you remove the polarization, but of course you are blind the first 5 hertz of the spectrum. But then if you compare the spectral density, the power spectral density of the blue signal in the bottom right image with respect to the singular values of the accelerometers attached onto the beam, and you have with purple the lateral accelerometers, and with black line you have the vertical accelerometers. You see that all vertical peaks that are present in the singular value plot of the accelerometers are also present in the power spectrum of the smart sensor, the cement-based sensors with nanotubes. So what we get here, and the first leading mode is quite evident, is that using these sensors, we can actually identify natural frequencies of structures. Of course, we have verified this also in embedded applications. So the sensors should be embedded into the molds before casting the concrete, and we have been doing this in different elements. For instance, on the beam that you see during curing time on the top right image, you see that there are some sensors embedded prior to casting, and on each sensor there is also a strain gauge to compare the measurement of the sensor with the measurement of the strain gauges. Then we have made an experiment like the one before, hitting the beam with a hammer, and you see like a typical vibration, decaying vibration obtained with the smart concrete sensors in the bottom left. Also, you see if a student goes on the beam and stays on the beam and then steps down and then steps up and so forth, loading and unloading the beam, you get very nice evidence of the increasing compressive strain through the output of the sensors in the blue line, while if you use the strain gauges, this is not so evident anymore. Strain gauges are with the red line. If we do dynamic measurements with the hammer, we get a good agreement between the sensor in black and the strain gauges in red, and we can verify that the leading peak of the first mode is actually well detected by the smart sensors. All these papers are cited in these slides, and most of them are with Dr. Alessandro as the main author. Another application we have proposed is when we use the smart concretes in bulk form. So the whole material, the whole element, maybe a critical part of the structure, like a node or something like this, is fully made of smart concrete. So here you see an example on specimens like the one on the top with different pairs of electrodes, or on a beam under 3-point bending. And we use the biphasic DC approach to do multi-channel readings and remove polarization. Here you see, for instance, what we get from the specimen on the top left, the results in terms of resistance along the specimen. You see the blue line in the bottom left image. You have that in the two outer contacts, we have larger resistance, but that's because of boundary condition in the diffusion problem of in the electrical problem. And then in the internal electrodes, we more or less have the same resistance. So the material is more or less homogeneous. And these values do not change in time unless there is a damage or something like this. So here instead you see the results of the application to the beam. So I go back to the previous slide. You see on the right there is a beam with reinforcement, only longitudinal reinforcement, no shear reinforcement, and this beam is fully made of cement paste with nanotubes. Then we have electrodes all through the beam, and the beam is simply supported, and we do something that is in between a 4-point bending and a 3-point bending. Let's say it's a 3-point bending test. So we increase the load that in this diagram is in the x-axis, and we measure the voltage drop across all pairs of electrodes that is in the y-axis. With the green line, you see what we get at the mid-section of the beam. So, of course, is where we have the largest variation in voltage, which means the largest variation in resistance of the material. And this variation in voltage drop is linear with the load until a certain point where we reach some plateau, a sort of, this graph resembles a little bit the plastic behavior of the cross-section. Then what is also nice to notice is that with black lines, blue lines, and red lines, we have sections that are located at symmetric positions with respect to the midspan. And more or less, they give consistent results because the problem is symmetric, apart from, of course, the random distribution of the electrical property of the material. But from the mechanical point of view, it's a symmetric problem. So we should see the same result on both sides, which actually is the case. And the third thing you should notice is that at certain point, when we are around 1.6 kilonewton, there was a shear crack forming out of the electrodes. And section number 1 and section number 15 show a behavior, an opposite behavior. One was increasing in drop, the other one was decreasing. And for sure, we have some bifurcation. We have some dramatic change in the behavior, in the electrical behavior of this section. And we will see later on that this is actually associated to the damage, and we can predict it with a numerical simulation. The same bulk application is the one we have made to this plate. So this is a bidimensional plate of cement paste with nanotubes that we have subjected to a series of impacts that generated progressive damage. Of course, in the video, the damage was already huge, but at the beginning, the plate was in sound conditions. And then we have a lot of electrodes placed on the other side of the plate, and we measure the voltage drops across all pairs of electrodes. And if you look at the results in the bottom right, you see in red the increase in the total resistance of the plate as a function of the number of impacts. So we have something that actually increases as we expect in terms of resistance with the number of impacts. If you look at the orange line, you see that there is a big change in the trend of the line at an early stage, so for a small number of impacts. In fact, this line is referring to a contact electrode that is close to an early stage damage. The green line instead shows a change in slope around 60 in impacts, so at the middle stage. And in fact, this electrode is located close to a middle stage damage. The blue line is referring to a location where we do not have any localized damage, and here we have a nice increase in resistance with increasing number of impacts. So what we can say from here, we have some change in the conductivity of the material due to the damage that we somehow can measure. Let's come to modeling, because if we really want to understand what's going on, we want to exploit the properties of these incredible materials for SHM, we need to be able to describe their behavior. So I will propose you essentially 2 or 3 techniques for modeling the behavior of these composites. The first one, and perhaps the most powerful one, is based on micromechanics approach. All these works, this is a series of papers that we have published together with Dr. Garcia Macias from my group. He's postdoc in my group, but also right now assistant professor at University of Granada in Spain. And he's a real expert in micromechanics. So what we have been doing was proposing a micromechanics framework for these materials. So what we do, we go from the nanoscale to the microscale and then to the macro scale to predict the average overall properties of the composite by some sort of homogenization technique. So for instance, we can predict, as in the equation you see in this slide, the conductivity tensor of the composite as a function, as a weighted average. Let me take this easy way of saying things, a sort of weighted average between the conductivity tensor of the matrix and the conductivity tensor of the nanotubes. Of course, where the weighting is based on the fraction of nanotubes, effective fraction because we are considering, so volume fraction, effective volume fraction because we are considering the interface between the nanotube and the matrix. But what's very important is that when we do this averaging, we have to consider the orientation of the nanotubes. So we do a sort of volume average of the properties of the nanotubes, considering their orientation distribution function, that is this ODF. Well, if we disperse the nanotubes randomly, this ODF is just 1 in all directions because we have the same probability of having the nanotubes oriented in any direction. But then if the material is strained because it's under compressions, for instance, then of course we will have nanotubes tend to align in certain direction with respect to others. So the orientation distribution function will change. What we've also introduced in this framework was considering the evidence that we have from our experiments. So like the nanotubes are not straight, they're sort of twisted, they're sort of bended. So we introduced these wavy nanotubes, and also nanotubes, whatever the efforts we make to make them be distributed in a uniform way in the composite, still we will have agglomerations, still we will have bundles. We will have this sort of ellipsoids in the matrix, and we have to consider those. So we have considered those agglomerations through the factors xi and zeta that are related to the relative volume of the bundles with respect to the total volume, and the relative volume and the relative amount of agglomerated nanotubes with respect to the whole nanotubes. Then how to consider the effects of strain? Well, when there is a strain, there is a change in volume. So there is a change in the volume fraction of the nanotubes, because of course the volume changes of the overall composite, but that's due to a change in the volume of the matrix, but the nanotubes do not change their volume really. Then we have the reorientation of the fillers, again, which we can analytically model. And these are typical results we get in terms of effective conductivity as a function of content of nanotubes for paste, mortar, and concrete. You see that there is this percolating behavior. But if we compare this with experiments, and experiments are the squares in this diagram, we do not really get a good match, even if we introduce the twisting of the nanotube. So we go from the purple line to the orange one, changing the angle theta from 90 degrees, that means a straight nanotubes, to 30 degrees, that is a very twisted nanotubes. Still, we do not really get close to the experiments. We get closer with twisting of nanotubes, but not really close. To really get close to the experiments, as you see in these results, we need to add also the bundles. If we add the parameters of the bundles, then we can really interpret the behavior of this composite. That was our result in a paper by Garcia Macias and co-authors in 2017. And this was systematically demonstrated for cement paste, mortar, and concrete. But as said, this model can also predict the piezoresistive properties. So we can predict the relative change in resistance or resistivity as a function of the strain. And we can see that the gauge factor is actually maximum at the percolation threshold, and actually follows the behavior you see in the bottom right. So there is a big jump in the gauge factor when we are close to the percolation, and then slowly it decreases again with increasing amount of nano inclusion. So it's very important to stay at the percolation, and if I may say, to stay a little bit over percolation, to have a material that is more robust with respect to not perfect distributions of the nanotubes in the matrix. And here we can show that we can well predict the gauge factors that we get from experiments, again with black squares, if we introduce the agglomerations besides the twisting of the nanotubes. And we see from the experiments that actually we get the maximum values of the gauge factors at the percolation. This framework was also extended to three-dimensional stresses and strains through a mixed micromechanics analytic approach and a numerical finite element simulation. This was also in a paper with Dr. Garcia Macias as main author in 2018. And what we got from this study was that the shear strain do not really produce big changes in resistivity. Instead, the material is sensitive to the change in volume. So basically, it's sensitive to the linear strains, but regardless of their direction, what we get is actually a sensitivity to volume changes, regardless of how we distribute the electrons. Another approach we have proposed for modeling the behavior of these sensors is by doing lumped circuits. Here we have lumped circuits means that we want to reproduce the behavior of these sensors by using resistors and capacitors in series and parallel, so equivalent circuits. And these are very good if we want to reproduce the dynamic response of these materials, like when we do vibration measurements. Because for the overall properties, micromechanics is better, but for dynamics, we need to add time into the problem. And the best way we found to do this was with equivalent circuits. We started this with Dr. D'Alessandro from my group that she was PhD. She got her PhD in these smart materials studies, and she continued working on this within my group up to now. And at that time, I think it was 2014, we proposed a first paper where we modeled these cubes by a resistor plus a capacitor and a resistor in parallel. And this model is very nice because it can reproduce the polarization pretty well, as you see in the bottom left. It can reproduce the presence of superharmonics in the response to a sinusoidal mechanical load, which can be seen by analytic derivation through manipulating the differential equation that governs the circuit. That is a linear differential equation, but has time-varying coefficients. But what we could not reproduce was the increasing frequency response function with increasing frequency. So a few years later, with Dr. Garcia, in another paper, collaborative papers with the rest of the group as co-authors, we proposed, let's say, an enhancement of the previous model, where we have noticed this. We have noticed that these materials, besides having a very strong piezoresistive behavior, they also have a little bit of piezoelectric capabilities. So if we look at the specimens and we apply a load, we see a change in the voltage. We see the material outputting a voltage change, so without any external input. So this means that the material is a little bit piezoelectric. So even if small piezoelectric effect, this is enough to modulate the frequency response function of these sensors and get increasing frequency response functions. We have shown quantitatively that this model outperforms the previous one, is more accurate in reproducing the response to a variety of loads, and it's actually more accurate in terms of frequency response functions, as I said. The last modeling method that I want to show you is based on resistor meshes. So it's kind of a lumped circuit approach. We reproduce the conductivity of the material through a mesh of resistors. This was work done with Donny and co-authors. Donny was at that time, Austin Donny was a postdoc in the group of Professor Simon Laflamme from Iowa State University. This great collaborator. We are working a lot in these topics together. And he was visiting, Dr. Donny was visiting my lab for some months, and we did quite nice research results, quite nice research. And one was these results I'm showing you now. So with this resistor mesh, we discriminate between contact resistors, internal resistors, and damage resistors to reproduce the effects of a damage in a structure. And we fit the properties of these resistors by getting experimental data and trying to get an optimal match between analytical predictions in terms of voltage drops across all pairs of resistors through this mesh model and experiments. The fitting problem is mathematically written in the bottom left of the slide. We take an average between the mean average error, a weighted average between the mean average error and the maximum deviation, and we try to fit this, minimize this cost function, and in this way getting the values of the resistors. Why this is interesting? If you look at the video on the top right, you see that we have a specimen with different pairs of electrodes. We measure the voltage drop across all the section, and we compare the analytical model in red, so the resistor mesh after calibration, with the experiments. So you see that after calibration, we have a good match. Then if we apply a damage, we apply a crack, there is no match unless in the model we include the damage exactly where it is. If you look at the top, you see the real damage in green. It's a crack. It's actually a cut. And in red, we see where we simulate the damage with our model. If you look at it again from the beginning, you will see that when we add a damage, we have a deviation. Let's see it again. Now we have a good agreement between experiment and model. Then we add the damage in green, deviation. Then we add the damage in red in the model. We move it. Now it's getting to the exact location. Okay, here is the exact location. And then it moves again. So with this approach, what can I say? I can say that we can, with this inverse problem applied to a resistor mesh model, we can actually detect and locate a damage in the form of a crack. Actually, I can show you that we can also track the severity of the damage. I cannot enter into the details, but if you look at the bottom right, you see voltage drop as a function of the cut length, and you see that this increases with the cut length. And model agrees with experiments with increasing values of the crack length. So we actually can track the severity of the damage. If you recall the experiment on the beam, where we saw this sudden change in voltage drop across section 15 and section 1, when there was a shear crack forming out of the electrodes. Here you see a comparison between experiments and numerical simulation. So you have to compare the continuous lines, black and red, that are experimental, with the analytical predictions that are also black and red, but they are dashed. So you see that there is not a perfect match, but for sure there is clearly the evidence that we get a consistent behavior between model and experiment. So when there is the crack, the two curves that before are overlapped, they just kind of undergo a sort of bifurcation. One goes up and the other goes down, and the same is predicted by the model. So from here we can say that yes, we have something that we can use for detecting and locating a damage, and also to progressively track its severity. To convince you once more, I can show you this other example, the example on the plate. You saw it before. We tried to fit the resistor mesh also for this plate, and then we produced a map of resistive values, the map of the values of the resistor constants. And you see in the right of the slide the results for the intact plate. Of course, you do not see a uniform resistance on the plate because we do not have a uniform material at the end. Then we have the damaged plate, where we apply the calibration procedure, the optimization procedure. We fit the inverse problem, and we get the map that you see in the bottom. And you clearly see the yellow spots in the middle and in the middle at the bottom, where we have the most prominent damages. We have some detachment of the material there. So maybe we do not really follow the cracks, but for sure we follow where we have some detachment of the material. If we take the difference between the map after damaging and before damaging, this is even more evident. And by the way, if you look at the temporal changes in one single resistor, see the left-hand side of the slide, then you see that the resistance actually increases with the number of with time, which means with the number of impacts. So somehow we are not only able to detect where the damage is located, but also to quantify its severity. All right, the second part, but I said it was expected to be shorter, of the presentation is about the use of smart bricks. So the idea a few years ago with some colleagues was within my group was, why don't we apply the same concept of smart concretes in the field of masonry? So we came out with this idea of smart bricks. A smart brick essentially is a clay brick that has piezoresistive properties, so it can work as a strain sensor within the masonry. The idea is to use this by doing static measurements, so no vibration measurements here. But what we want to do is taking measurements from smart bricks, periodically, and if there is an earthquake, we compare the post-earthquake with the pre-earthquake conditions. And of course, we can do this automatically. And what we expect is that if there is an earthquake, then there are cracks forming in the structure, which means that the loads change their ways from the top to the foundations. So it means that under dead loads, we will have changes in permanent strain within different portions of the structure. And we can construct a map of the strain field, construct a map of the change in the strain field, and see where most changes are located, and that could be the location of the damage. And we could use this to extract features to detect, locate, and quantify the damage. This is more or less the idea. Regarding the approach, in theory is the same, but in practice it's much difficult to have a smart brick because the brick burns. It's in the fabrication process it goes up to more than 1000 Celsius degrees. So for sure we could not use carbon-based inclusions unless we do very special treatments that, however, are expensive. So one possibility we proposed was to use titanium dioxide, that even if they are not really conductive particles, and by the way, they are spheroidal, so not best for percolation, still they could enhance the piezoresistivity of the material. But the best results we get are with micro steel fibers made of a special alloy that keeps a very high electrical conductivity even after burning in an oven. And this is how we fabricate the smart bricks. As a matter of fact, these smart bricks have a very nice percolating behavior. You see here we go from 1 times 10 to the minus 9 to about 1 times 10 to the minus 3 Siemens per centimeter in terms of conductivity, with an amount of microfibers that goes from 0 to 5% with respect to the weight of the clay before burning. So a very nice percolation. And by the way, there is a double percolation because there is a percolation at around 0.25% and another one around 2%. Well, actually, if we look at the microstructure of these materials, for instance, through scanning, through X-ray tomography, these scans were made at the Technical University of Braunschweig in the framework of a collaboration we have with the group of Professor De Laurentiis. We saw that actually the microstructure is quite complicated. We have microporosity, we have microcracks, we have iron particles and other metals dispersed in the matrix besides the fiber. So this may justify the double percolation, even if it's something we have not yet studied in details. By the way, these kind of tomographies are very useful to ensure that the fibers are well dispersed, and we also compute a dispersion index to be sure that the composite is made properly. In terms of modeling these bricks, for these bricks we have proposed a model that is a series of resistors, because we have some contact resistance that is also sensing, because the contact here is the plate electrode made of copper typically. And of course, this is going to be sensitive to the load, especially at low compression stresses. Then, of course, we have the internal change in resistance due to the piezoresistivity. So we have a model that accounts for the two phenomena through a series of resistors. And this model shows that from the experiments, we can say that below 1.5 megapascal of compression, the sensing capability of the sensor is governed by the contact, while above 1.5 megapascal, it's governed by the internal piezoresistivity. And by the way, this model fits very well the experimental results and shows very consistent strain measurements with respect to what we measure with strain gauges. So coming to some structural applications, here you see one first application of a wall, small wall, under in-plane loading with 3 bricks. What we did here was increasing the load until provoking some damage. On the top, you can see that if you apply a load, there is a change in the response of the brick. So in the sound conditions, we can actually track the load intensity. But if you look at the middle figures, where you see the normalized change in electrical resistance of each single brick divided by what we read at the mid brick. So essentially we divide the output of the 3 bricks with respect to the output of the middle brick. And we reproduce these results at, we measure these results at 20 kilonewton, 50 kilonewton, and 70 kilonewton. We see that from 20 to 50, there is no change in the results. And this is something we expect from the theory if the material is in the elastic range, even if it's cracked, but it's in elastic conditions under compression. We do not have any sensitivity of the normalized change in resistance divided by the change in resistance at the mid brick to the load. But then at 70 kilonewton, we have a crack forming in the wall. And in fact, we have a large deviation of brick number 3 with respect to what we read in the previous steps of the test. So for sure, we have something sensitive to the load and we have something sensitive to the damage. To go more into this, recently with the work of Mr. Meoni, that is a PhD student from my group, we are going towards the use of smart bricks to do dense sensor network. So a larger number of smart bricks within a masonry structure. We reconstruct the strain field through an interpolation procedure using kriging, that is a stochastic interpolator that's very interesting from several perspectives. And then we do damage localization through the definition of different features that essentially look for locations where the strain has large gradients, which means that probably there is a crack in that location. That's why there is a relaxation of the material around the crack. That's why there are gradients of strain there. And in this way, we try to locate damages. These features for locating damages were proposed in a different context in a work by Professor Laflamme and co-author together, where I was also co-author in a different context. So here you see an experiment of this type of approach to a wall under in-plane loading. I apologize, I will be like 5 minutes longer than the 45 minutes expected. I hope this is not a problem, but I would like to show these final results to you. We apply the load on the right side of the wall in eccentric position, and we induce some damage. In this slide, you see a comparison between the real damage, real cracks C1, C2, and C3 observed on the structure at different loads, 15, 25, and 50 kilonewton. And below, you have a numerical simulation that resembles very well with a micromechanics approach the experiments. And if you look at the strain field from the numerical model, you will see these are the strains at the different load intensities. Then we interpolate the strains from the smart bricks. And what we find with the Krieg interpolator is a map like this. That makes pretty much sense with respect to the finite element map. Of course, with the smart bricks, we have an averaging of the strain between mortar and bricks, because actually we are measuring the strain of the bricks and then we are averaging it. With the FEM simulation, the FEM simulation, of course, you have strain that is different from the units, the bricks and the mortar. But still, we can say that there is high consistency between this map and this map. If we do the same with the strain gauges that are attached on the smart bricks, we get maps that do not really make much sense. The strain is much more localized than in reality. Let's say if we take the finite element simulation as a replica of the reality, which is due to the fact that the strain gauges are very local in the measurement they provide. If we do this damage location with this damage locating feature, you see that with the smart bricks, we are effectively locating crack C1 and C2 when it's forming and when they are progressing around 25 kilonewtons. And the only crack we cannot really detect is crack number C3, that is a flexural crack, but this is very unlikely to develop in a real structure. If we do the same with the strain gauges, the location of the damage is much more challenging, and perhaps only at 25 kilonewton we can say that something is going on in the region where we have cracks C2, C1, and C4. Another interesting experiment that will go very quick here was on this building, testing on a shaking table with some smart bricks at the base. With the measurement is the same you have seen. We have done numerical simulation, and we have defined a sort of damage index that is that considers the relative change in absolute relative change in strain that we have at single brick and in the total bricks with respect to the undamaged situation. Here you see the real damages after different earthquakes from the shaking table. On the right, you see the simulation that is somehow consistent, satisfactorily consistent with the experiments. And here you see a comparison between the real damage, that is the gray color, so undamaged is white, negligible to slight damage is light gray, moderate damage is moderate gray, substantial damage that, however, is far from the ultimate limit state condition. I have to say we never reached collapse here, but not really. We do not even get close to collapse. Is darker gray. You see with the red line as a function of the different seismic inputs. So you see what we get from the experiments in terms of damage index. And with blue, what we get from the numerical simulation. So you clearly see that we have an index based on the output of smart bricks that can give us a quite nice ability to track the intensity of the damage. At least we can say, yes, there is a damage, and yes, the damage has progressed, or no, the damage has not progressed after an earthquake. So let me conclude this talk by saying that nanocomposite materials such as smart concretes with multi-wall carbon nanotubes and smart bricks with steel microfibers are very attractive materials for the future of structural engineering. They can sense the strain, and they can allow damage detection and localization. It's very critical to disperse the nano or micro filler in the proper way, because otherwise we do not reach the percolation and we lose what we are looking for. To model the behavior of these materials, typically you need to apply different approaches, from micromechanics to lumped circuits to resistor mesh models to series resistor models and so on. But with these modeling approaches, you can really understand what's going on and have an effective processing of the data towards an effective SHM. So in the last experiments, I hope I have convinced you that these smart materials can highly outperform traditional sensing technologies like resistive strain gauges, because these materials have a more direct damage to signal relationship that, if you recall, was the initial purpose in the introduction, that I said in the introduction of this work. A little bit of references from our group. Of course, this is the results of a lot of collaborative papers. For a reason of time, I couldn't mention some of these papers, but they are all here. And of course, you are all welcome to send us emails and contact us anytime for questions. If you want to have any clarifications, we are more than happy to discuss any aspects. Here are a little bit more references. I went from the newest ones to the oldest ones. Of course, again, this is a collaborative work, so I have to acknowledge the part of the group that is the group of Structural Health Monitoring and Earthquake Engineering Lab at University of Perugia. My group, that is, I have to acknowledge the part of the group that is devoted to smart materials. So Dr. Antonella D'Alessandro, Dr. Enrique Garcia Macias, Mr. Andrea Meoni, and Mr. Borke Birgin, that is also working in this field, is developing a Marie Curie PhD thesis on smart pavements. Today, I didn't have enough time to show you how to bring this concept into the smart pavement field, but maybe this is going to be for the next time. So let me acknowledge also Professor Laflamme from Iowa State University, great collaborator, great colleague. And at that time, he was his postdoc, Dr. Austin Doney, now assistant professor in the USA. And of course, the sponsors, just mention a few, European and national project that sponsors this research. And with this, really, I thank you very much for your attention, and I close my presentation. Thank you very much.